Okay, so let's recall where we were before the hurricane interrupted us. We were talking about minimizing quadratic functions. So we have a function of an n vector f of x, and it's of the form x transpose k x plus b transpose x plus a constant. And we wanted to minimize this function. And we saw that the way to do that was to take the minimum is the value x star, which is equal to k inverse applied to the vector b. And that is, of course, provided that the inverse exists, which is to say k is positive definite. Well, it has to be positive semi-definite for any minimum to exist, and then the inverse requires the definite condition. And now we're going to give an important application of this, which is called least squares. And least squares is the following problem. I'll just draw it in 2 dimensions. A least squares problem in R2 is you're given a line, L, and you're given some fixed vector B. And what you want to do is find the closest point in the line to the point B. So that is, if you take all of the points in L and you calculate their distance, there's one which minimizes that distance, and that's this one here. And the problem is to find this point x on L, which minimizes D. Okay, so the question is, how do you do this kind of calculation? So that is to say, suppose you're in Rn, and you have an m-dimensional plane, and a point, and you're trying to find this this distance d. So you have this m-dimensional plane, let's call it P, and suppose P is given as the span of a bunch of vectors, V1 through Vm, and there are m of them because it's m-dimensional. And so the way we've learned to think of such a thing is that P is the range of the matrix A, where the VI's are the columns of A. Okay, so that is to say, the vectors in P are the anything that you can write as A applied to X, where X runs over all of Rn. Right? That's what it means to say the range, and this is just another way of saying A times X is a linear combination of these vectors V1 through Vm. And we're given this vector B, and we want to minimize this distance. Well, that is to say, what we want to do is we want to minimize the length of AX minus B. Okay, so this is a crucial point, so let's pause here and think about this for a minute. What I'm saying is let X run over all of Rn, and then this AX is giving you all of the vectors in P, and I'm saying the one that you want is the one for which the length of AX minus B is minimum. So that is to say, for example, if this was AX, then AX minus B is this vector right here, and the length of that vector is what we're interested in. And of all of the vectors in this plane P, this is the one, I'll call it X star, which minimizes this this length. And let's write this as the inner product of AX minus B with itself. Well, we're minimizing, it's a square actually, but minimizing this and minimizing the square is the same thing. So let's just put the square in there, and we can say what we want to minimize is this. Okay? And the point is, if you look at this for a second, this is clearly a quadratic function in x. When I work this out, because of this x here and this x here, I'm going to have some sort of x squared term, roughly speaking. And when we work it out, it's going to be a quadratic, and we can apply the previous, what we learned previously. So let's go ahead and do that. So let's see how this works. So remember, we're in Rn, and we have this matrix A, which is some number of vectors, m. So it's an n by m matrix, where these are the vectors vi, however many there are. And we're also given vector b, which I'll write as b1 through bn. And we're trying to minimize this inner product, ax minus b with itself, ax minus b. And let's just stare at this for a moment. What is x? Well, x is just an m vector, x1 through xm. These are giving you the coefficients of these m vectors, and this is giving you a point in the plane. And so let's just do a little sanity check here. This product here, this is an n by m matrix applied to an m vector, and this is an n vector, and everything in sight is an n vector. And of course, this inner product here is whatever given inner product we have. And so let's, to get the ball rolling here, let's suppose that this is the usual Euclidean inner product, which is to say VW is just V transpose W. And work out what you get here. Well, so then what you get is AX minus B. AX minus B, I'm tired of writing the arrows, so I'm not going to write them anymore, is AX minus B transpose times AX minus B, which is to say X transpose A minus B transpose, all of these things transpose, times AX minus B. All right, remember the transpose is the transpose of the terms, but you change the order here. And when you write this out, we're going to have 4 terms. And so the leading term is going to be X transpose A transpose A X. Okay. And then there's going to be 2 other terms, one from here and one from here and one from here and one from here, which gives you X transpose A transpose B minus X transpose A transpose B, and then the other one is minus B transpose A X. And then the last term is just from here is plus B transpose B. And in case the colors are giving you headaches, I'll just switch back to black and write this as X transpose A times X. Now, let's look at these terms here. We've seen this kind of thing before. these two things are actually equal. They're both scalars, and they're the same. And so I can just write that as minus 2 x transpose A transpose B. And then the last term is B transpose B, which you might think of as norm of B squared. Okay, beautiful. Notice that this is exactly the kind of thing we've been talking about. This matrix here is symmetric because it's of the form A transpose A. Now, it may or may not be positive definite, but never mind that for the moment. It's symmetric. And then we also have another term here, which is this term you can think of as being X transpose times the single vector 2A transpose B. And then this is the constant C. And this is exactly the kind of minimization problem that we've just discussed. What a coincidence. All right, well, so let's sum it all up. How do you minimize this function? So this thing here is what we've been calling K, and I'm going to call this A transpose B vector F. And what I conclude is the following result. In the case when the inner product is the usual Euclidean one, then the minimum is given by X star is equal to K inverse applied to F, where K is this matrix A transpose A, and F is this vector A transpose applied to B. And I'll draw the picture. This is this B, and this is the point X star, and the actual distance, which I'm calling D, is given by simply the norm of B minus X star, and that turns out to be the square root of the length of B squared minus F transpose K F. So let's just look at this for a minute. So this is saying you compute the length of the vector B minus X, and I'm saying that turns out to be simply the length of B squared minus this thing, which is some number, and it's like the inner product of F with itself, the length of F, except with respect to this matrix K. Okay, well, let's just, I'm just going to conclude now with a variant, which is what do you do if this is a general inner product, not just the Euclidean one, which is to say VW is equal to V transpose CW, where C is some arbitrary symmetric positive definite matrix. And the answer is it's almost exactly the same. The way you minimize this function is the same formula, K inverse applied to F. The only difference is that now K is A transpose CA, and F is now A transpose CB. And how's this different from what I had before? Well, the only difference is that this term C here, in the previous case, C was equal to the identity, and now that's an extra factor to take into consideration. Okay, I'll do some examples in class if it ever stops raining, so see you then.